It's time.
We don't speak anymore of war. We don't speak anymore of war. We don't speak anymore.
To finally return the volley at Päpä Flammy. You thought your differential equation would make a difference, huh? Well, I've got the best kind of generalization for you today, and it's called Analytic Continuation. Because we're going to finally find out what the harmonic numbers really are. Why do they have this weird number attached to them, this Euler-Mascheroni constant? Where does that come from? How does it relate to the harmonic numbers? We're finally going to see, not just in some obscure infinite sum, or some weird finite sum involving binomial coefficients, or some odd integral involving some weird version of the Riemann zeta function. We're going to find out what the harmonic numbers are today. And that's my generalization for you, Päpä Flammy. And you're going to like it. And since you said that you figured out that generalization of the nth degree homogeneous differential equation, I'm going to present for my next attack, after this one, a genuinely novel result that I came up with in the beautiful and interesting and quite puzzling subject of graph theory. And I will, at some point, once I finally learn how to typeset in LaTeX, I will write it up as an actual paper, because it's a genuine result of mine. But that'll have to wait, because I've been waiting to build up to this one for a while. So welcome to Euler-Mascheroni episode 10. Welcome to the destruction of my contemporary. So today I need to define a certain thing so we can use symbols a little later on. We're going to define the harmonic numbers today to actually be lowercase h of x. That's how we're going to talk about the harmonic numbers. So harmonic numbers. Right? These are the harmonic numbers, h of x. And capital H of x will be the antiderivative of little h of x. So we're going to have capital H of x such that the derivative of capital H of x equals little h of x. And so we're going to need that today, because we're answering the very, very lovely question. What is the integral from 0 to n of the harmonic numbers? Right? This is not a trivial question to answer, but the argument that I'm going to make for what it actually is sort of a discrete argument, one that really only works for integers, but then you will see what function we actually end up with using these integers, that we can just simply extend it to the complex numbers using a beautiful analytic continuation of the function that we will see. And so I hope you're all ready for this answer, because it's a beautiful, beautiful answer. So what we need to do first is do a little bit of separation. So we actually know what part of this integral is equal to, because I did this in one of my videos, and I showed that it was equal to another definite integral that Päpä Flammy had shown was equal to the Euler-Mascheroni constant. So we know that this is equal to, we can use the sum, we can use the linearity of the integral, so we know that this is equal to the integral from 0 to 1. I guess this isn't linearity. Linearity would be adding the integrands, not the indices. But we know we can break this up into two pieces. We know that this is equal to the integral from 0 to 1 of the harmonic numbers, plus the integral from 1 to n of the harmonic numbers. And now we need to do a couple of cosmetic changes. We know that the xth harmonic number in the original definition is the previous harmonic number plus the next reciprocal, right? So we know that what this is actually equal to in here is h of x minus 1 plus 1 over x, right? That's like sort of the definition of what the harmonic number is, right? It is equal to, and that goes for actually any x, right? If you start with the h of pi, right? The next harmonic number, one unit away, is that plus 1 over pi. That's the beautiful thing about it. That definition always holds no matter what the input is, right? Every harmonic number that is 1 away from any input is always the sum of the next reciprocal, right? Of the number that's 1 above that. So if x in here is pi, and we have the pi minus first harmonic number, then we can just add 1 over pi to get the pith harmonic number, right? And that's just how that works. It's a general definition that always holds, because that was the original definition, and we showed that other functions were equal to that. And that works with complex numbers, except of course with the negative numbers that we can't input. And today we're really going to see where that comes from, not just from the recursive definition of the harmonic numbers, but today we're going to really see why that's the case. So now we can do a couple of things. We can break this integral up into 2 pieces. So that's exactly what I'm going to do. So I'm going to break this up into h of x minus 1 dx, and I'm going to add that other integral, the integral from 1 to n of 1 over x dx. And by the way, because this is an integral, what we can do is call this capital H of n, right? This is the antiderivative, like I said at the beginning. But it's capital H of n minus capital H of 0. But what's capital H of 0? Capital H of 0 would be plugging in 0 here, and taking the integral from 0 to 0 is 0. So we don't actually have to worry about capital H of 0. We can just call this capital H of n, right? Technically, it's capital H of n minus capital H of 0, but you can imagine plugging 0 in for n, and you end up with the integral from 0 to 0, which is, of course, 0. So we do not need that as part of it. So remember, I changed the notation. Little h is the harmonic numbers, and capital H is the integral or antiderivative of the harmonic numbers. So we know that this integral is equal to h of n. And so now we have 3 separate integrals that this is actually equal to, and we can sort of write down what these things are equal to. Notice, this is just the integral from 0 to 1 of the harmonic numbers, and this was the integral that I was talking about, where I showed that it was equivalent to another integral that Päpä showed was equal to the Euler-Mascheroni constant, 0.577, right? The limiting difference between the harmonic numbers and the natural logarithm. Notice here, we have the integral from 1 to n of 1 over x. What is the antiderivative of 1 over x? It's the logarithm of the absolute value of x. Well, since x is strictly positive here, we understand that this is actually a definition of the natural logarithm of n, right? And so we know that this piece here is the natural logarithm of n, by definition. And notice something here. What I can do here is I can plug in x plus 1 for x. And if I do that, all I have to do is reduce the indices by 1, right? Because I'm inputting something that's 1 larger, so I simply have to shift the whole function to the left by 1, and I still get the same answer. So if I plug in x plus 1 for x, I just end up with h of x again. But I have to now shift both of the indices down by 1. So it goes from 0 to n minus 1 now. But if you notice, take a look at this integral. This is of exactly the same form as this integral right here, except now the input is n minus 1, which means that this integral is not capital H of n, but capital H of n minus 1. Which means we have just derived a recursive definition for the integral of the harmonic numbers. Capital H of n is equal to the Euler-Mascheroni constant plus capital H of n minus 1 plus the natural logarithm of n. Because we have that recursive definition, I can apply that recursive definition to this term right here. Isn't that really neat? So I can keep the Euler-Mascheroni constant, and I'm going to change the middle term, and the natural logarithm of n stays as well. But notice, we know what h of n minus 1 is. It's going to be the Euler-Mascheroni constant plus h of n minus 2 plus the natural logarithm of n minus 1. Right? That's what the recursive definition allows us to do, is break it up into the next term. And now we can combine things again, and we'll end up with 2 times the Euler-Mascheroni constant, plus the natural logarithm of n, plus the natural logarithm of n minus 1, which is the same as the natural logarithm of n times the quantity n minus 1. So we'll end up with plus h of n minus 2, plus the natural logarithm of n times n minus 1. Right? I hope everyone's following that so far. I'm just using the recursive definition for capital H of n that we just derived, right? This is capital H of n, the integral from 0 to n of the harmonic numbers. And maybe I just have to apply this one more time for you to see how this is going to work. So I'm going to apply the recursive definition to this. We have our 2 gamma right over here, and this can be rewritten as gamma plus capital H of n minus 3 plus the natural logarithm of n minus 2, and then we're adding this natural logarithm term on the outside, right? I hope that's all visible. I should really have started writing to the left more, but essentially what's going to happen is we're now going to have 3 times gamma plus h of n minus 3 plus the natural logarithm of n times n minus 1 times n minus 2. And as you can see, this is just going to keep going down and down and down as a recursive definition. So we're going to get 3 times gamma, and we're going to end up with the natural logarithm of n times n minus 1 times n minus 2, right? And this is just going to keep going down, 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 down. And so really all we have to do is just plug in n for this, because it's going to take n steps to get n to go to 0, right? We have to go n steps down. And so what we end up with, folks, is after all of these recursive definitions again and again and again. So what we end up with after doing all of these recursive steps again and again is we end up with n times the Euler-Mascheroni constant plus h of n minus n. I'm taking this to n steps, right? This was the first step, and then I'm doing the whole steps n times, so I end up with n minus n, and I will simplify that, plus the natural logarithm of n times n minus 1 times n minus 2, and after n steps, remember after the first step we subtracted 0 from n, so at the nth step we're going to subtract n minus 1 from n. So we get all the way down to the product of n minus 1. And now we can do some simplifications. This is h of 0. And we know what h of 0 is. That's when we plug in 0 in the upper index of this integral, and we're taking the integral from 0 to 0, which is just 0, right? So this is 0. I hope that's clear. And now what do we have? We have the natural logarithm of the product of n times n minus 1 times n minus 2, all the way down to n minus 1. But what happens when I distribute this negative? I end up with negative n plus 1. And what's n minus n? N minus n is 0, which means the last term of this product that's always decreasing by 1 is 1. And what do we call the product of every number of every integer from n all the way down to 1? We call that n factorial, which tells us that the integral from 0 to n of the harmonic numbers, capital H of n, is equal to n times the Euler-Mascheroni constant plus the natural logarithm of n factorial. Isn't that f***ing something? Isn't that amazing? Let's recall something. Capital H of n is an integral, and it depends on this upper index. And we have something called the fundamental theorem of calculus, which allows us to figure out what the original integrand was, simply by differentiating, right? Because we know that this is equal to h of n, which is a function, minus capital H of 0. Capital H of 0 is just 0, so taking the derivative of it is 0. But the derivative of this with respect to n, now sort of thinking of n as a continuous variable instead of an integer, allows us to do something really nice. But what I first want to do is I want to realize something. We're going to rewrite this as the Euler-Mascheroni constant times n plus the natural logarithm of, and this is where the continuous part comes in. Because what is the generalization of the factorial function to the complex numbers, other than where it's undefined? That would be the gamma function, right? The gamma function itself. So we have little gamma along with big gamma now, because the factorial function is equal to the gamma function of n plus 1, right? And now what we're going to do is I'm going to write this up here, and I'm simply going to take the derivative. And so what we have is that capital H of n, the integral from 0 to n of the harmonic numbers, is equal to the Euler-Mascheroni constant times n plus the natural logarithm of the gamma function of n plus 1. First we need to consider one more thing. Consider just the natural logarithm of gamma of x. No, consider the derivative of the natural logarithm of gamma of x. Well, given that we know how to take the derivatives of things with natural logarithms, it's simply 1 over the inside function times the derivative of the inside function. So this is going to be equal to gamma prime of x divided by gamma of x. And this is a very, very, very special function. This is the di-gamma function, the logarithmic derivative of the gamma function. And can we recall when the gamma function is undefined? The gamma function is undefined at non-positive integers, right? Which means the original factorial function is undefined at negative integers, right? It's defined at 0. It's the 0 factorial is 1. So we know where this is going to be undefined. This is going to be undefined at non-positive integers. But if we shift it up by 1 like we're doing here, that means that the gamma function of n plus 1 is undefined at negative integers, exactly like the harmonic numbers. And so it shouldn't really be a shock that these are somehow related to the gamma function or the factorial function, because they're undefined in the exact same places that the gamma function slash factorial function are undefined. So all we have to do to figure out what the harmonic numbers are equal to is to simply take the derivative with respect to n here. So we end up with the derivative of capital H of n, the integral, the antiderivative of the harmonic numbers, which is equal to the harmonic numbers, since we are taking the derivative. What's the derivative of a constant times n? Well, the derivative of a constant times n is just that constant. So the derivative of the first term is just the Euler-Mascheroni constant. And now all this is the derivative of the natural logarithm of gamma plus of n plus 1 instead of just n. So what we end up with is still just the derivative of the gamma function of n plus 1 divided by the gamma function of n plus 1, which, using our definition of the digamma function, that means that this is equal to little gamma plus the digamma function of n plus 1. But of course n can be continuous variable at this point, because that's the point of the gamma function, right? It is an analytic continuation of the factorial function to the rest of the complex plane where it is well defined. And so now, my friends, we have finally the final definition of the nth harmonic number, or however you want to call it. And now I'm going back to the original. And you know what? I'm going to use a z, because this is it. This is the complex definition, right? The zth harmonic number, which we know to be the integral from 0 to 1 of 1 minus t to the z over 1 minus t dt, or the sum from k equals 1 to z, if it's an integer, of z choose k, times negative 1 to the k plus 1 over k, or the sum from k equals 1 to infinity of z over k times z plus k, or the integral from 0 to z of the Hurwitz zeta function of 2 comma x dx. We know now the final definition, that this is equal to the Euler-Mascheroni constant plus the digamma function evaluated at z plus 1, where z is the complex number that we're trying to find. And we have finally found a perfectly well-defined analytic continuation of the harmonic numbers. And this is incredibly important, because this allows us to define the values of the derivative of the gamma function, right? This allows us to define those values. So, what can we do? Let's take a look at what we can do. What does this tell you, by the way? This tells you that the harmonic numbers and the digamma function, which is the logarithmic derivative of the gamma function, plus 1, with the input of z plus 1 instead of just z, this is just saying that the harmonic numbers is simply all the numbers that are the Euler-Mascheroni constant more than the digamma function of z plus 1. Which is really quite amazing, right? It's simply a constant number plus another amazingly special function that gives us the harmonic numbers. A beautiful, beautiful fact. This also tells you that if we take the derivative of this with respect to z, we end up with the Hurwitz zeta function of 2 comma z. That tells you, what does that tell you? That tells you that this is actually the derivative of this thing, usually denoted digamma 1, right? That would be the second derivative of this thing, right? Because this is the first derivative of this. And so if we differentiated this, and we would end up with this fact, that the Hurwitz zeta function of 2 comma z is equal to the digamma sub 1 of z plus 1. Right? And all this is the derivative of this function. And so we finally have our analytic continuation. And now we're going to use it to solve for a few values of this function. I really hope that people either saw that, either worked this out on their own, or are at least surprised that this is actually what it's connected to. It's connected to the logarithmic derivative of the gamma function, as well as little gamma. So it's got big gamma and little gamma. What a beautiful combination. And so all we're going to do now is we're going to evaluate some of these values. We're going to figure out some of these values, right? So what do we know? We know that the gamma function is well defined at non-positive integers, so we know that the gamma function of z plus 1 is going to be well defined at all non-negative integers. So we know, now, this is what we know, right? We know that the harmonic numbers are equal to the Euler-Mascheroni constant plus the derivative of the gamma function at z plus 1 divided by the gamma function of z plus 1. So let's derive a couple values. Well, we know what h of 0 is. H sub 0 is 0, which still has to be equal to the gamma function, the Euler-Mascheroni constant, plus the derivative of the gamma function at 0 plus 1, which is just 1, right? 0 plus 1 is 1, divided by gamma of 0 plus 1, which again is just 1. But what is gamma of 1? Gamma of x is just x minus 1 factorial. We know that 0 factorial, which is 1 minus 1, is 1, right? Which means gamma of 1 is just 1, which tells us that we can eliminate the denominator because we're just dividing by 1. But then we can simply subtract gamma over, and we find out that the derivative of the gamma function at 1 is just negative Euler-Mascheroni constant. Isn't that something, right? All I did was subtract that over, and that's the fact, right? The slope of the gamma function at 1 is negative Euler-Mascheroni constant. Isn't that quite cool? Well, we have one more value that we can quickly check out because we know what another very simple value of gamma is. We can plug in 1, right? All these pens are running out of ink. We know that the first harmonic number, h1, is just equal to 1, right? And we know that, again, this has to be equal to the Euler-Mascheroni constant plus the derivative of 1 plus 1, the derivative of the gamma function at 1 plus 1, which is of course just 2, divided by gamma of 1 plus 1, which is of course gamma of 2. But what is gamma of 2? Again, the gamma function is x minus 1 factorial, so this is the same as 2 minus 1 factorial, or 1 factorial, which is just 1. So again, gamma of 2 is just 1, which tells us that subtracting the Euler-Mascheroni constant over tells us that the derivative of the gamma function at 2 is actually just equal to 1 minus gamma. Isn't that neat? So we're actually going to see this number quite a bit. So let's quickly write down what 1 minus gamma is approximately. So this is about 1 minus 0.577, right, which tells us that it's about 0.42278, So that's about 1 minus the Euler-Mascheroni constant. And we're actually going to see this appearing in two different forms in the next video because I'm going to show you two amazing things that are exactly equal to 1 minus gamma, and I think you'll find them very, very enticing. So, given that we were able to finally derive a general analytic continuation of the harmonic numbers, we were also able to show the values of a couple of the derivatives of the gamma function. Later on, after I do the awesome stuff involving this constant here, of 1 minus the Euler-Mascheroni constant, we're going to consider what it might mean to ask, what are the fractional values of the harmonic numbers? So like the half harmonic number, the third harmonic number. By third, I mean the 1/3 harmonic number, or, things like that. So we'll have to consider that in a little while. We know that the 1/2 one will have to do with something to do with the square root of pi, because gamma of 1/2 is either the square root of pi or the square root of pi over 2. I don't exactly remember. But Päpä, behold my beautiful analytic continuation of the harmonic numbers. Let's see what you got next, buddy. Quick little thing, this channel has an Instagram, so it is at whatthehectagon, of course, and it has a Twitter, and it is of course naturally, also at whatthehectagon. And my email is the incorrectly spelled whatthehectagon, why spell check before you make the email right, that you can't then change, at gmail.com. Now all of these are in the description if you don't want to have to somehow watch the video and pause it and actually write it down. That's the stuff. Thank you for watching, and bye-bye.